In this video, we're going to look at some common errors when programming in C, specifically if using the C89 standard, and I also will give you some solutions to the problems. In the many years that I've taught programming classes, I would see the same types of errors over and over again. For this video, I'm compiling using GCC, but note that none of these problems are really a GCC problem. It's just that the particular error messages may be specific to GCC. If you're using a different compiler, these are still mistakes, but the actual error message that you see may differ slightly. So let's start with this first one. So I'll try to compile, and I get an error message. And technically it's giving me a warning. So if I were to look, it did compile, and it did run and do what I wanted, but the warning says ISO C90 forbids mixed declarations and code. In C89, which is equivalent to this C90, variables must be declared at the top of a block. So that means this really needs to be here. And so now when I try to compile, it compiles without any warnings. Right? So just remember, declare the variables at the top of the block if you're compiling using C89, which is what I'm doing. This right here for me is an alias that I've set up so I don't have to really type all this, but it's equivalent to typing GCC space dash ANSI dash, space dash pedantic. All right, so that's the first one. Let's look at the next one. This is an actual error, and it says C++ style comments are not allowed in ISO C90. The problem is that in C89 or C90, there's only one comment style, and that's to begin with / star and end with */. So now it compiles out problems and runs. Third one. This one is a logic problem, and so therefore it was actually difficult for me to replicate, and in fact running this now may not demonstrate the actual problem because it's one of those sometimes it shows up and sometimes it doesn't problems, but it's still technically wrong. Now here things worked as I intended. I want to sum the integers from 1 to 4, and so their sum is really 10. The problem is I didn't initialize sum. And note that the compiler didn't give me any kind of warning. Now some compilers will catch that, but in this case it didn't. So what happens is when I say int sum and don't initialize it, which technically is what's happening with I here, but I doesn't matter. But when I say int sum semicolon, I'm getting a spot in memory, and whatever bit pattern is at that spot is what the initial value will be. So in this case, I wanted sum to be equal to 0, and by sheer luck, that bit pattern was equivalent to 0. But I may run this program again, or somebody else may compile and run it, and I may get a different initial value, which messes up everything else. So really, I should have done this. Now, I doesn't matter because when I use it, I'm going to initialize it here to 1. So this is what I should have done, and I get the same results, but that's, like I said, due to sheer luck. There's no guarantee that every time I compile it, I'm going to get those same results. All right? So that's a logic error. Logic errors are very difficult to track down because syntactically, this is not wrong. It's just not what I want to happen. Let's see what happens here. So here I have x equal 5, and then I'm asking if x is equal to 99, print, really I should say this, print x is We'll compile it. This is another logic error, so it runs fine. X is 99. So what happened here? I said X was 5, but when I check, it claims it's 99 and prints this message. We'll only use one equal sign here. So this is an assignment, which means now I just change the value of X to 99. And this in turn, this part right here, reduces to a value of 99, which is true. Because it's 99 has a truth value of true, and 0 would have a truth value of false. So really I should have done this. Put 2 equals, so now I'm doing a comparison instead of an assignment. And now we say X is not 99. So let's see what happens here. This is going to be a syntax error. Do that again so we can see it more clearly. So it's an error, it won't compile. Array size missing in D. When I allocate memory to store something, I always need to in some way let the computer know how much memory to allocate. Here for X, I didn't explicitly say I need to store 3 ints or to give me, in this case, 12 bytes because it's 3 times 4. So the computer will count how many numbers there are here and allocate enough memory to store those. But because I don't give any values here to D, it's relying upon me doing something like this, where I say, give me enough memory to store 20 ints. And then when I try to assign a value to the first of those positions, now it worked. So it compiled. I don't print or anything, so we can't see anything, but it compiles fine. So the problem is they're not telling the computer how much memory to allocate by doing this. This is another logic error, so the computer doesn't help me out here by telling me what the problem is. So down here I say X is equal to 5, and I print X is 5. Then I pass S to this function where I want to add 99 to it, and then I return and print what the new value of X is, but it turns out there is no new value, it's still the old value of 5. Well, the problem is I didn't change the value because this X up here is not the same as this X. So I have a couple of options. One would be do this, reassign X to the original value, and then I need to change this to return X, and this of course should be int. Now it's 104, that's one option. Another option would be use a pointer, so I'll pass in the address, and I could use the same variable name, but to make it more clear, I'm going to say P as the variable name, which means now I need to say star P. And now it is 104 again. So that's the solution of that. So here's what it was before. Here I have a pointer, and I give it the address to the first element. So I want to add something to this, or excuse me, I want to have the pointer here now point to the new thing and print what that is. But when we run it, we see that doesn't work the way I hope. And in fact, it even gives me a warning here. Now, I've seen compilers, including probably older versions of GCC, that wouldn't warn you here. They wouldn't tell you I'm using this incorrectly. And so it does technically run, because that's just a warning. What I intended to do was change the address in pointer to now point to this. So the problem is, if I want to change what's stored inside this pointer to now have the address of the 99, I need to have a pointer to a pointer here and pass in the address. So I can do this. Pass the address of pointer, which means this now needs to store the address of an int. And star P now is working with this block of memory. Oops, and what's the problem now? So this would need to be this as well. And now I put 99. So I have the, well, excuse me, I mean, I didn't store 99 here. I stored the address for the 99 in PTR. And so now it points at this. So originally PTR has the address of the 1. Now PTR has the address of 99 and things work. But that's a logic error, not a syntax error. I like to write scalable code, which means that I don't want to hard code very much. So I may want to have a function that does something with an array, but I don't necessarily want to hard code to the size of the array. So I may use something like this: columns equals size of D, which is the size of the entire array in bytes, divided by the size of one element in that, which should give me the number of columns. Let's see what happens. So let's give me some warnings again. It does run because it's just a warning. So it says down here in main, D has 6 elements. Up here it claims it has 2 elements. Then down here, or excuse me, but X up here has 7 elements. That's right. So the problem is the 2 elements. What happened? Well, when I pass D, I'm not really passing D, I'm really passing the address of the first element of this array, because this is a one-dimensional array. So I pass the first element of the array, which happens to be an address. So this right here is equivalent to writing this. The compiler changes it into that. And so it actually liked me changing the syntax here because of the way I used it. So it didn't give me a warning, but it still has the same functionality, right? It still doesn't work correctly from my perspective. So what happened, I passed in an address. Well, in this computer, an address is 8 bytes. Well, D sub 0 is an int, which is 4 bytes on my computer. So 8 divided by 4 is 2, which is why it says I have 2 numbers. So what's the solution to that? Well, I need to do something like this. I need to say columns and say int size and then print something like this. And this works fine because X is created here. So now I get 6 elements and 6 elements for this. Let's see what happens here. So this is a runtime, what I call a runtime error. So it compiles, but I get a segmentation fault. So I didn't state this at the beginning, and I should have. But the errors, as I'm discussing them, fall into 1 of 3 categories: syntax errors, logic errors, and runtime errors. So what's the difference? Syntax are things that are syntactically incorrect. For example, this needs to be terminated with a semicolon. So if I take that off, it won't compile. And it tells me I'm missing something. That's just syntactically illegal. So I can't do that. It's easy for the compiler to catch those kind of things in general. Logic errors are where I do things that are logically correct in the terms of, or excuse me, they're syntactically correct, but not what I want. So let's say I see a formula in a book, and the formula is A is equal to B plus C. But what I write in my program is A is equal to B times C. Well, it's perfectly legal to say B times C, but that may not be what the formula is supposed to be. So the compiler can't tell me this is wrong because it doesn't know really what I'm trying to do. That's up to me as the programmer to know that I'm supposed to use a plus as opposed to a star because I'm supposed to do addition instead of multiplication. So it can't catch things like that. Now, runtime errors, I would say, are really a type of logic error, but they cause problems when you're running. So syntactically, they appear legal. They're just not things that I'm supposed to do. And so in that sense, they are logically incorrect, but they cause the computer to, or the program to crash or something like that, which is what we'll see here. So let's see what we get here. And so I run it and I get a segmentation fault, which usually means I'm trying to do something with memory that I shouldn't be doing. So the problem here is that cat here is what we call string literal. It is stored somewhere, but it's not stored in S. S is a type char star. So it only contains the address to the first letter of this string. And so I think technically the C89 standard says what happens here is undefined behavior. But in general, this will be written someplace I should not try to modify, and therefore when I try to change the first character to a capital X, that's when I get the segmentation fault. In this case, cat was stored somewhere that I don't have permission to change. And so doing this would try to change it, and therefore it causes a problem. So really what I should have done if I want to change that is do this. Now I've allocated memory for the letters in cat as well as a terminating null, and I can legally change those this way. And so I get zat instead of cat. So don't change string literals even if it is legal to do. This is another difficult error to catch in many cases because, at least with older compilers, they didn't necessarily catch this for you. Here it is catching it and telling me that I'm doing something wrong, but they didn't always catch it. So sometimes they show up as runtime errors. So what's the problem? Well, I created this string that appears to only consist of capital X. But this is, you see that with the double quotes, this is a true C-type string, which means that I stored a capital X character followed by a terminating null. So in fact, I could have written it like this. That's perfectly legal. It's just a lot more work on my part. So that in itself is not a problem. The problem is down here, I'm trying to see if the first character is an X. And so I use single quotes here, which is giving me the first character. But text is the address of the string. And string compare expects to get the address of a null terminated array of characters and another address of a null terminated array of characters. So that's why it's showing me it's supposed to be char star and char star are the two types, but I'm not giving it that. So I'm really comparing it to this address to this character, and that's wrong. If I'm really trying to see if the first character is an X, because it's an int, I need to do a straight comparison. So really I need to do something like this. And the messages themselves don't match up. But it is legal code. Let's fix this to right. So that's legal. And this is correct. Right? But the problem was this. Using string compare, to compare characters. Right? So here I have a pointer that contains the address for the 99. And then I'm going to try to increment the 99 by 1 to make it 100 and then print it again. But let's see what happens. Compiled fine. And actually ran. So syntactically it's all correct and I don't generate a runtime error. The problem is one of logic. Look at what happened. Pointer, I changed the address in the pointer variable to now point at the 123 instead of changing 99 to 100. And the problem is right here. If you look at the precedence table, you can see that the plus plus, when it's used as the postscript version, that is, it comes after the variable, like here, that has higher precedence than the dereference operator, the star. So this sees the plus plus first, and it thinks what I wrote, I don't need parentheses here, but I'm putting them in here now to make it more clear on what it does. It says, oh, well, increment the address being pointed at, and then use what's there. Although it does the increment after it used it. So technically, so let me go back and rephrase that. It does use what's there, but then afterwards it increments the address. So it didn't increment the value. The problem is I'm not doing anything here. So then when I get here and say star pointer, I'm now using the new address. So if you want to increment it by 1, I do this instead. Or you could do plus equal, but I could do the other one. Plus equal 1. Whoops. Did I compile this? So really, excuse me, this needs to, I get rid of this. Have redundancy there. So now it went from 99 to 100 because I never changed the address. I'm still pointing it at this spot in memory. And so you can see here D0 is 100, and the pointer also points still at that same spot in memory. I actually prefer this anyway, even if you're okay with using the other. It's just the opportunity to use it incorrectly is too great for my liking. So I prefer just do this anyhow. Runtime error. Let's see what this does. Compiles, and I get segmentation fault. So what I'm trying to do here is copy this string over into temp. But the problem is temp only stores an address. And I am giving string copy an address, so I'm using this correctly. The problem is there's no memory at that address for me to use, or at least I'm not authorized to use it, which is why I got a segmentation fault. So what I really need to do is allocate memory. So if I'm using temp like this, that means I'm probably intended to use dynamically allocated memory. So what I needed to do before the string copy call was this: temp equals malloc. And I need to allocate some memory. So one way to do it would be use string length to get the size of S, but that only counts the characters as I see them. So I also need room for the terminating null. So I'm going to add +1 to get enough room. And now I allocate memory, or I compile it and run it, and it works. So what I did here was attach some allocated memory to temp, and now I copy S into that block of memory that I was given, and then it works. Before, temp just had some bit pattern. Maybe it was 0, maybe it's something else, I don't know. But it's highly unlikely it's an address that I have access to, so therefore I got a segmentation fault. But it was entirely possible I could have gotten really unlucky and the number that was here was a valid address for me to write to, but because I didn't allocate memory here, I shouldn't have been doing it anyway, so it's still wrong. Segmentation fault. So what happened here? Here's buffer, stores this string. Here's text. I do allocate memory to store this as a string because 50 is more than enough bytes to store this. I want to print the address of this, but notice I can't even do that, so I'm going to have to do some work here just to show you how the program was supposed to work. Although this address won't be the same next time around. Oops, sorry, I was compiling the wrong program. Let's go back and do this again. So it won't be a runtime error, it's a logic error. So I get this address stored in text, but then when I say what's the address stored in text, it's this, because this was the address of buffer. And we can see that here. So let's do some more formatting to fix that, make it look like. So that's address stored in buffer. So what happened? Well, this is legal, and there's times I may wish to do this, that is have a pointer to a character array. But what I was attempting to do was to copy the buffer into another array, this one being dynamically allocated. But what I did was I saved the address to the T here, and I just lost the address for this block of memory. So I actually also created a memory leak. So now I have no idea where this was at. So it's all syntactically correct, didn't generate a runtime error, but if I had more code that was actually doing something, like trying to free up this memory, that might generate a runtime error. Let's do this. Yep, runtime error. Because I didn't free up this block of memory, I don't know where it's at anymore. I attempted to free buffer, which I can't free anyway. So this is wrong. So what's the solution? Well, do this. Or excuse me, I want to do a copy, so string copy from buffer into text. And we can actually print here. Just to prove it. I'm doing that to make it jump out as being obvious that which one I'm printing. This is a string, so I'm printing from text. And you see the address in text remained what it was initially for this block of memory. So this is the correct way to do it. Copy buffer into the new array instead of just saving the address. And I think this is the last one, so let's see what happens. So the idea here is I have this file, data text, and it consists of 4 lines. And I want to store the first token on each line. And so what I do is I create a buffer here to read a line from the file. So initially it will store 1 string. And then I have an array here that can store the addresses of blocks of memory. And then I'm going to go through, tokenize just once to get the first token. That's all I need to do. Save the token, I think. It's not really correct. And then come back and see what I saved. So let's see what happens. This is a logic error, not a syntax error. 4, 4, 4, 4. How did I get 4 4s? Well, what did I actually save here? We're looking at this line. I didn't save 1, 2, 3, and 4. And even though it says 4, I didn't actually save 4. What I saved was the address stored in token. Because when I say T to counter, you see T is of this type, char star, which is the same thing as token. And so all I did was store the address stored in token. But what address was there? Well, the address for the first token on each line is going to be B sub 0. So really, if we look at this, in fact, let's do this. I'm going to change this. And this will be, sorry, T sub I. See, it ends in BA00, BA00. All I did was store the address to the first character location in buffer each time. And so then when I get to here and say print that as a string, well, the very last thing in buffer was for string. And when I tokenize it, I actually put a terminating null at the delimiter position, which is the space here. So each time, since I store the same exact address, I just print what's at that address the same exact time. That's what I did. So what should I have done instead? Well, like the previous problem, I need space to store the token. So I really should have done this. malloc string length, what's at that address, +1 to give me space also for the terminate null. And now do a string copy. And this would be tcounter token. One, two, three, four. So now I really did save the tokens that were on each line instead of just the address in the buffer 4 times. And so now it works. So in creating this video, I did this after creating the other videos in the series, but I'm going to put it in the playlist so that you see it early. Now, if you are watching it at the point where I think you should see it initially, I've just shown you a bunch of things that don't make sense, because if you already know all this, you wouldn't have to watch my other videos on how to program in C. But hopefully you've made it this far in the video, and then as you get to these different things, you'll come back and review the video or avoid the mistakes in the first place if you can remember. But it's highly likely you're going to make some of these mistakes. I still make some of these mistakes, but I've certainly seen these mistakes over and over again from people who are new to programming in C, or just new to programming, period. And so hopefully this will save you some debugging trouble. All right. If you find videos like this helpful, please hit the subscribe button.